sei.
Ok, so
Deixa eu chegar lá. Bom, acho que...
I think we are good. We can get started. So, as usual, we start with one student presentation. We will hear about lattice gauge theories. Pretty good.
Right. So the idea here will be sort of to give a few examples of where lattice, or the more common applications of lattice on the numerical side of things. I think so, yeah. Okay, so if we think about it, what are some nice applications in principle, right? Things that are particularly hard to compute with usual QCD that we can sort of exploit the numerical ideas, right? One of them is hadron masses, right? These are bound states of QCD which are very in the deep non-perturbative regime of the theory, which in principle starting from usual QCD, we don't really know how to compute them. And this is sort of a nice place to start, right? So hadron masses, right? And the idea goes as follows. Well, we have some hadron, which is characterized, I think my computer slept, maybe I'll just, given hadron, we'll have some set of quantum numbers which define it. And we look for an operator which shares this set of quantum numbers, which we call an interpolating operator, right? So some O, right? So for example, think of positive pion. You'd have something like, I don't know, some for y plus. You'd have, for example, d gamma 5 u, right? So it's a scalar, pseudo-scalar, right? And then this we assume it will have some non-trivial, some non-zero overlap with the hadron state we're interested in, right? So consider then, so some O of x, right? So consider then the propagator, or the correlation function produced by an operator like this. So something like 0, O dagger, 0, 0, right? This time evolution of this is generated by the Hamiltonian, right? So e to the minus ht, O 0, e to the minus ht, right? O dagger, right? So if we introduce a resolution of the identity here on energy eigenstates, right, we can write this as a sum over n of 1 over 2n en. Oh, and the action of this is trivial on the vacuum, right? So you have something like, when this acts, hits the energy eigenstates, you get something like e to the minus energy, right? So en t. And then you have something which is a matrix, the absolute value of a matrix element here. So we have this, right? If we look at very large times, in principle, this should be dominated by the smallest energy, right? Which is the ground state energy of our hadron, which is its mass, right? So really, in the large t limit, this should look like something like b e to the minus m of this hadron t, right? Right. And then in principle, if we can compute this numerically, we can fit something like this and extract the hadron mass of the hadron we're interested in. And indeed, if we do that, we see something, like, yeah, I'm not sure. Let me see if connection. Screen mirror. Well, I don't know. I can show my screen if it's.
dele invernou e não voltou.
Deixa eu deixar ela acesa.
Tá voltando.
Ah.
Ele vai achar o final.
Tá ativado. Ué.
Vou achar a configuração aqui.
Acho que não é nada disso.
Cadê aqui?
Eu acho que... Deixa eu ver se eu choose content. Ah, talvez assim? Vamos ver.
É que você colocou o aplicativo. É melhor screen na próxima vez.
Tá. Foi? É, agora ele tá tentando.
Se pegar um pendrive, a gente coloca no outro.
Eu acho que... Ó,
Fica melhor.
ok. Ele vai pegar um pendrive e tentar colocar, não sei se... Vai demorar um pouco. Ah. Right, posso, em princípio sim. Acho. É só que é mais legal ver que, de fato...
Aqui na gente também?
Não, esse é pendrive?
É.
Não tem. Eu desenho, não tem problema. Eu desenho. Bom, tá.
Cadê o teu save as?
Você conectou o pendrive já?
Sim.
Dá lá ali. Aí vem no Finder aqui.
Nossa, que
É.
Só que isso eu vou conectando no projetor.
Pronto. Esse Lattice Plots. Já tá no pendrive. Já,
Tá vendo como que é, né? Problema. Tem como explicar, entendeu?
Aham.
A gente é puramente uma questão técnica de sistema.
Right. Próximo, volta. Aí, não, volta. Aí, tranquilo. Obrigado. Right. So that... deixa eu...
Se quiser,
beleza.
um zoomzinho ali.
Obrigado.
De cima.
De cima, tá. Okay. Right. So that doesn't really look like an exponential, right? But this is just an artifact of the fact that we do this on the torus generally. So you have a backwards contribution which corresponds to going the other way on the torus. So this the other contribution will go like mh t minus t, right? So it dominates the opposite end of the time, and which is why, and then it's symmetrical around the t/2 axis, which is what we see there. But we'd like to know really how big does the time need to be, right? Because if it's too big, then well, maybe our lattice isn't big enough and we can't really reliably make a plot that we'd like. So one way to go about this is to look at an effective mass, right? So you define an effective mass, right, which is really just the log of g of t plus 1, right? This just compares how quickly this it just looks for the variation in this exponent, right? And t plus 1, because remember we're in a discretized lattice, so t plus 1 is just the next exponential. And if this is constant, then we're in a good region in principle, right? And indeed, if we, let me see if yeah, right. So that's the second plot. And really, remarkably, we have most of the region is good, right? From maybe like 4-ish up until like 26. You have your contribution is dominated by the ground state, whereas in these 0 to 4 and 28 to 27 to 30, they're dominated by the excited states. So this is nice, right? And indeed, in these regions, we can fit these exponential contributions and determine the mass, which is what's done on the left plot, right? So this is one really nice application. Another one that's fairly similar in principle, but it's technically a bit different, is, well, maybe if we want to understand confinement especially, it would be nice to look at the potential between a quark and an antiquark, right, at some given distance. And so how do we do that? Well, so this is what's called the static quark-antiquark potential, right? So given some antiquark and a quark separated by some distance r, right? What's V of r? Right. The idea is very similar, but now we have an extended object. So clearly an operator like psi dagger 0r and psi bar, right, 0, 0. Wouldn't work because this is not cage invariant, right? So what we need really is something like this. You have one quark here, and they're connected by a Wilson line, and the other quark at the other position, right? Now, if we have this, we have sort of our gauge invariant trial state or interpolating operator, right? And we want to propagate it in time and look at the behavior of this for large t, right? And so what do we do now? Well, recall, so you have some, I'll call this t just to be safe. So quark here and antiquark here, right? But recall from Pedro's lecture that the fermionic part of this propagation can be expressed as something like this, right? You have a path integral over the path, and then an exponential over minus m square root of y dot squared plus, well, something like this, right? But remember that we'd like them to be at the same position in the end, right? Because we're really looking for the expectation value of this potential at fixed stars. So we take these masses to be really big. In this situation, then the path integral over the path, the path integral over the path will be dominated by the stationary contribution, right? And in this situation, then what remains is really just this and an exponential of e to the minus t, right? mt, which we can just ignore. It'll be some normalizing constant, right? So really, this propagation gives me another Wilson line. And in the end, what remains will be a path integral over A of this object, and then the other Wilson lines, when in the end this closes a loop, right? So really, what measures our V of r for these fixed masses is just the expectation value of the Wilson loop, right? And hence, and this should go for large t as some e to the minus spoilers. Some e to the minus v of r times t, right? The potential we want is something like minus 1 over t log of v of r, or the expectation value of the Wilson loop, right? So do we have a good ansatz for this? And the answer is, well, naively, yes. One, we expect a contribution that's Coulomb-like, so something, well, first a normalizing constant, right? But then some Coulomb-like contribution. But there's also the confining aspect of this, right? We expect that for large R's, the energy should increase, right? Because they want to stay together. So really, but that could be R squared or cubed or whatever, but it can't, right? Remember from Pedro's lecture what we know about the confining behavior of the Wilson loop. We know that in the confining regime, this should go like something that's suppressed by the area of the Wilson loop, right, to first order. But the area here is just R times t, right? So we expect something like this as well, right? And then if we take the log 1 over t, this is a linear contribution in the potential, right? This is why people often talk about, well, the confinement has a very defined potential, which is linear in the distance, and it's really the same statement as the statement that the Wilson loop should be proportional to the area. It's just expressed in another way. So really, this is an ansatz, right? For given what we know, what this should look like, and indeed, we get exactly that, right? You see that for we see that for low R, right, you have some 1 over R contribution, and then after some point, the linear contribution dominates, right? And this, I can give sort of a, if you'd like later, a picture of what happens if the quarks are a bit more dynamical in the propagation, but so it's just an I can give a sort of qualitative picture. I can't really give a very precise mathematical one. If you'd like, we can discuss it later. But yeah, these are the general ideas that I thought were nice to present.
Thank you. Question?
Go ahead.
Maybe can you pass the microphone?
Hi. Thank you for the presentation. That was very nice. It might be a simple question, but this is not my field. Why would you expect that Coulomb kind of contribution over there? I understood the linear contribution in the potential that they derived under there, but why would you expect the Coulomb-like behavior?
Well, it's really what you clearly see it. Well, let me just do this step by step. For perturbative QCD, you see it, right? Because it's really a consequence of the abelian part of your QCD, if you'd like, right? If you look at low G, for example, right? You'd expect that the gauge transformation is something like your abelian plus small, right? So you expect a Coulomb-like contribution. Why it holds even for non-perturbative scales is it's a good question, but let me see if I have a good picture for it. I mean. I'm not 100% sure. I think, well, maybe, I don't know.
No, it just does not. So I think the correct way of writing the potential, I would not, I mean, it's just relabeling of the constants, but I would say I would write AR plus B plus C over R plus D over R squared plus dot, dot, dot. So what we know is that at large radius, it grows linearly. Then there is a constant. Then there is 1 over r, 1 over r squared. That's just corrections.
Right. Fair.
So this 1 over r is just the first correction that you will be able to see. If you had better numerics, you would see a 1 over r squared. And then with better numerics, you would see a 1 over r cubed.
Right.
It's just that the effective theory to leading order, it is just a long flux tube that grows linearly. But then you just have infinitely many corrections. Of course, there is no reason to expect this potential to be simple. This is not the form of the potential.
Right.
The potential is just a complicated function that at large radius behaves linearly. And so we just make a Taylor expansion at infinity and keep the first 3 terms to fit some plot. But then from the plot, the main things you want to check is that the string tension, which is C, match with other computations. What were these papers? You did not mention what papers you picked, why did you pick these papers? You just showed some plots, but what were these papers? And can you tell us a little bit why you picked these papers and not other papers and so on?
So when I was sort of looking for what to present, the thing with fairly modern papers about these types of things is that either they'll be sort of very, well, how do you optimize this to be better? So for example, some papers talk about how do you choose your interpolating operators to make the overlap maximum so you have better numerics and all that. But so I sort of took a step back and I thought I looked at. Actually, these are from different papers, both of these. I got them from one book on lattice QCD, which is really what this whole thing is based off. It's a chapter, parts of a chapter of a book on an introduction on lattice QCD, which I thought was pedagogical and sort of showed the very basic applications neatly, which is why I chose it. I can show which book it is.
No, that's fine. One technical question. So when you showed the plot with the plateau in the middle,
right?
You said some words about the vacuum. You said for small times and for late times, the vacuum is contributing. Then it's excited states. You said some words like this. I did not understand what these words meant.
What I mean is, so if you ignore sort of it's better to sort of think of without the sort of identification of the torus. But generally, if you're not on high enough T, right, then the domination of the ground state is less pronounced generally, right? And this is generally just what's happening there. Well, for very early T's, the suppression of time isn't sufficient, so you see the excited states more. So and hence the effective mass, which is really the measuring. It's measuring how different the next one is from the other one. Is more pronounced in the middle, so or in the beginning. So you'd like to wait a bit so the suppression's stronger and you have a better approximation.
I think you said, when you said, I think you said it the other way around. I think you misspoke. You said some words. I think you said it the other way around, so I was confused.
Sorry.
What is the label M there? M equals 002, 005.
Those are the masses as computed by fitting. And then the other one has an effective mass on the y-axis, which is measuring that, the plateau region or the log, right? So one is the fit, the one they got from fitting, and the other one, the y-axis of the second plot is this.
Yeah, I don't believe that. Can you think again? I doubt that's true.
I mean,
maybe it is true, but I really doubt it.
I mean, I don't know. That's what what was claimed there. I don't know. Maybe it's you want to say that.
Okay, so let me understand first one thing. So first, why do we call this M effective?
That one?
Yeah.
Because
what's the relation between this M effective and the physical masses?
Right. So suppose you're in a region where you can ignore.
Yes.
So then you have something like.
No, I know the answer, so you can speed up. You can
Right.
just say,
It's just you'll have a t+1, and then this factors out the t
Right.
contribution, and you have a mh. Right. So if it's constant.
So the answer is, what's the relation between M effective and
They're the
M?
same.
They are the same. Okay.
Right.
So M effective and the masses, this is just a way of extracting the exponential, right? So
Right.
the masses are the same.
Yes.
Okay, so now if we look there, we
yeah,
see the green
I see your
curve
point. Yes.
and the red curve, and the green curve is 0,2, and the
Right.
other one is 0,8. It's not what's matching there.
Right.
Even if you say it's a rescaling factor, they differ by a factor of 4, not by a factor of 10. So I think your statement is wrong, clearly. These masses are not the outcome of fitting that.
Do you know? It's probably. Oh, let me think a bit. It might be because once you. Let me think. Yeah, once what the chapter does actually, it sums these contributions, the backward propagation and the forward propagation. It sums it together, and then it actually resums the geometric series of when it wraps around more than one time. And then it gets sort of a more complicated general expression for M, which is probably, it might be why, but in principle
No.
it should be the same, yeah.
No, that's
Yeah.
a very small effect, of course.
Yeah.
No, if you see a plateau, no.
Yeah, I'm not sure.
No, that's not the explanation. Also, imagine you look at this plot, and you tell me, oh, I made a fit and I got 0.20. Then I made another fit, I got 0.10. Doesn't it make you suspicious?
Right, it's probably, yeah, okay.
These numbers are very perfect.
Yeah,
it's really
yeah,
amazing.
it
You
looks a
run
bit,
numerics
yeah.
in a cluster and you get 0.20 and 0.10.
Yeah, you're right.
Maybe they want to reconsider what these masses are.
What they are.
Yeah. How could these numbers be so perfect?
I
How
mean,
could
it's probably...
you fit, you
wanna
run some numerics and you got 0.10. Then you wait for another month, the numerics are working, and then you get 0.05, which is exactly half of 0.10.
Right, it's probably you want to say that it's generated by sort of simulation, just for it's generated by the expression directly, or
So when we have numerics, typically we get very ugly numbers.
right.
Or we get nice numbers. What are the nice numbers in the numerics and what are the ugly numbers?
The nice numbers in
Yeah,
numerics.
which ones are the nice ones and which ones are the ugly ones? Because clearly there are ones that are nice and ones that are ugly.
I'm not sure what you mean.
The nice ones are the input ones.
Ah, right,
The ones
okay.
that I decide.
Right,
I will do the
right.
numerics with
Right.
this length,
Okay.
and I pick nice numbers that I like.
Sure.
Okay. So do you want to?
It's probably they probably generated from the expression, the fit, right? It's you want to say it's just illustrative, or
No, I suspect these are quark masses. Given some quark masses,
right.
you
It
give
might
some
be,
quark
actually.
masses, and then you simulate. If the quark masses take those values, what would the pion mass, which is non-perturbative, what would be the mass of the pion?
Ah, right. It might be that.
So
actually,
that's
yeah.
why they inject some nice quark masses, 0,
Right.
0.2, 0.5, 0.1, 0.2.
Right.
And given
right.
those quark masses, they estimate the mass of the hadrons.
Right. That makes sense.
That's
yeah.
probably what this is, but I'm guessing.
Yeah, that makes sense. Yeah. Yeah. Just well, yeah. A nice picture that I don't know if you as I thought I said I'd mention. I'll just mention it qualitatively. Sort of what happens when you make this quark seed dynamical is that eventually, as they separate and the energy increases, you get that famous effect of flux tube breaking, right? It eventually you have so much energy that you generate a quark-antiquark pair, and it separates into 2 mesons instead of 1 meson. Yeah, that's just sort of the
Yeah. Okay, very good.
okay.
Thank you.
Thank you.
Okay, so
Ah.
Okay. So did you guys have time to have a look at the paper? Yeah. So so let's write the first equation of the paper, and then what I will do is I'll spend half of the lecture explaining the origin of that equation, and second half exploring the consequences of that equation. Okay, so we start with the first equation of the paper that says that the free energy of a spin glass system that we are going to define, and the statement is that the free energy is equal, so we are writing equation 1, is equal to the extremization over some variables Q, A, B. So you have to maximize some quantity over some variables Q, A, B. Okay, so take the derivative of this expression, impose that this is 0, of the following expression, which is T, the temperature, times minus beta square over 4. So this is the temperature T, sometimes we can use beta, plus, and then there is a funny thing going on here. There is a limit when an integer n goes to 0 of 1 over this integer n. And then we have an expression here that we are going to write that, strictly speaking, this expression makes sense for n equal 1, 2, 3, 4, and so on. And we are thinking of this expression as analytically continued from these integers, and we are promoting this expression to some function of n, thinking of it as if it was a real number. That's a tricky thing, but that's the way what we are instructed to do. Let's write something, but think of that something as a function of n. In other words, imagine you are powerful enough to compute it for any n, then you would write it as a function of n, and then you have to continue it to n equals 0. Okay, what's that expression? So the first term, for example, is the following: 1/4 of the sum from A and B from 1 up to n. So you see n terms. Of course, saying n goes to 0 is a bit tricky. What exactly do we mean by this? Of Q AB square. So that's one term. And the other term is minus logarithm of the trace. This trace stands for summing over a bunch of spins that are plus minus 1. How many of them? There is an index A, and there are n copies, 1 up to n. So again, this makes sense when n is an integer. So it's a sum over how many terms here? So there are 2 to the n terms, right? Because we have n copies, and each spin can take 2 values. And so we sum over these 2 to the n terms a simple expression, which is exponential. So some free energy of these small n spins, which is a sum of A and B up to n. As we said, there are n copies. Beta square, and then spin A coupling to spin B. And as we said, the coupling between them are these constants A and B that we have to extremize over. Plus, if there is an external magnetic field, beta H times SA. Okay? So first, this is, if you want, the expression. So the claim that the starting point for Parisi, that if you want to compute the free energy for this spin glass, this is what you should do. Maybe there is an overall minus sign, I suspect. Is there an overall minus sign? No, it's okay. Okay, right. So any question about the definition and the starting point, the statement? So this is equation 1 of the paper. And as I said, what I would like to do is, so first we will do some analysis of what leads to this equation. And then we will analyze what comes from this equation. Okay? And of course, the challenge of this equation is that we are dealing with some matrices Q that are n by n matrices, and we have to extremize it, do it for any n, find the function of n, analytically continue in n, and send n to 0. And that's tough, right? Try to make sense of this. Or we could try directly to think of these matrices with n being some kind of continuous parameter and try to take the limit n to 0 before. Okay? And so as we will see, the punchline is that 0 by 0 matrices are infinite dimensional matrices where there is lots of space to put lots of stuff. And so as soon as you continue from integers to continuum, then matrices, they become basically linear operators, and there's infinitely many stuff that you can put there. And so the suggestion is to try to think of this Q as an infinite by infinite matrix, even though it's 0 by 0, full of blocks and hierarchical structure, and that is an ansatz for this Q. Once you make an ansatz, you minimize within this ansatz, and you ask, was the ansatz good or not? Okay? And so the main thing here is what is called the Parisi ansatz. So if you want, it's a way of parameterize Q in some way, plug that parameterization here and get something, and that something is an analytic function of n that then you can analytically continue. So, okay. So that's the key thing. And that's a very inspired ansatz. It's a very clever ansatz. And this ansatz is inspired by the physics of this spin glass, which is what I'm going to review a little bit before. Okay. So even before we start reviewing that, let me just remind you of some basic things. One is, if we have a partition function is the sum over all configurations. And then we have e to the minus 1 over the temperature times the energy of these configurations, like in the previous presentation. And of course, in practice, we can think of our spectrum that there are many, many, many states, right? And we can always think of some energy and energy plus delta energy. And think that instead of summing over the states, I sum over the energies. I count how many states there are with a given energy in a given bin. And that's what we call, this is the definition of the entropy. And then e to the minus beta times E. And then in practice, in thermodynamics, this will then be dominated by e to the minus beta times the free energy as function of beta, where the free energy is just the energy minus the temperature, which is 1 over beta, times the entropy, where this energy and temperature are extremized to minimize this free energy. And so this gave me this tells me what the energy is and the entropy is. Okay? So that is just dominated by the saddle point of the integral over the energies. Okay? Okay. And so in particular, we see that when we expand, when we look at the free energy, we recognize these two terms. So as an example, for example, the entropy is equal to minus the derivative of the free energy with respect to the temperature. So if you compute the free energy, the derivative of the free energy with respect to the temperature gives me the entropy of the number of states. Okay? And the energy is equal, once you know the free energy, if you want the energy, well, the energy is just the free energy plus T times the entropy, and the entropy we saw is minus, so minus T dt of F. Right? So if you know the free energy, after you know the free energy, you can compute the energy and the entropy as a function of the temperature in this way. Okay, it's just some very standard thermodynamics things, just so that you remind yourself of these notations and so on. A second thing that I just want to remind you, so that we don't lose time when we get to that point, is that often in thermodynamics and in other contexts in physics, maybe you found it in quantum mechanics, solving some well potentials, we will be doing some computation, and at some point we have to solve some transcendental equations of the form m equal hyperbolic tangent of alpha m, where m is, say, some magnetization, right? Now, how do you solve this equation? Well, one thing you do first to see if there is a solution is to plot this tangent, and tangent hyperbolic is something like this. And then you plot m, and you see that there are solutions here. But here it's important that when drawing this tangent, I assume that the slope here is bigger than 1. Right? So this solution, so there exists a solution m star if alpha is bigger than 1. If not, there's no solution. So sometimes the solution is just m equals 0. Sometimes there is a solution m not equal to 0. And in some models, the existence or not of that solution would be a way of detecting some magnetization that starts to appear when you change alpha. Right? So in this case, if you would plot m as function of alpha, m would be 0 until alpha is 1. And then when alpha is bigger than 1, I start getting some magnetization. Okay? So this is some common manipulation that often appear. Okay. So having said that, what is then our spin glass? So we'll start by saying, what is this for the spin glass? Okay. So let me write it here maybe. So the model we want to study is the following. We want to consider that Z is defined as a summation over a bunch of spins that take values plus minus 1. I runs from 1 to capital N, which is a big number of spins. By the way, the free energy is an extensive quantity. So when I wrote this, this is not the free energy. This is the free energy per spin. So if you want, I should put an N here. So this would be the free energy, the full thing. And this would be the free energy, the free energy would be N times this, sorry, I should just say here. I should call this small f. And so this is capital F divided by n. Okay, so it's really the intensive quantity that makes sense. So this z is a summation over all these spins. And then we have exponential of a summation over all the spins, 1 up to n. So first there is a trivial term, which is the magnetic field coupling to all terms. In practice, this term here, we think of h equals 0, but maybe a small value of 0. Just some tiny value. In case there is some Z2 symmetry that we need to break, we imagine we had a very infinitesimal magnetic field. It doesn't play a role in what we are discussing. The interesting part is the next one, is the sum over all spins I and j. And then we have a coupling between spin I and spin j. And these guys are random with a probability distribution P of j, which is equal to 1 over okay, with some random distribution. So each jij, I randomly pick, and I pick each jij, and then and that's it. And this j is actually, this variance is actually very small. And that's crucial because you see that you are summing up to n terms. So naively, this energy is here, it's quadratic, would be n squared. So the only thing this could be okay is if these j's are on average very small, so that we have n squared terms, but each of them is on average 1 over n. And so we get a quantity that on average, that overall is scales appropriately. Okay. Now you see that this z, of course, depends on the j's, right? You took a random set of j's, and this defines a z. You randomly pick another set of j's, you get another z. So each time you want to compute z, you should generate a set of couplings. So it's like a piece of material. So you have your material. It's a bit misleading to draw it like this because there's no locality. I's and j's, they talk to each other. So I should really think of these links. There are connections in all possible directions between everyone. But the point is that each coupling here is random, right? So here there is some jij that's random. Okay? And so I run my simulation, I pick some random couplings, each coupling is picked randomly, and then I have a material. Maybe I run once, and I got lots of positive couplings here, lots of negative couplings here, lots of very small couplings over there, and so on. And then I take another rock, and the rock is slightly different. But what's important to have in mind is that when you have a very big material, when you have a very big piece of material, and you want to ask for some average physical quantity, the very big piece of material is a sum of many very big pieces, like this, and this, and this, and so on. So when you take a rock of this material, where all the couplings are random, and you ask for some macroscopic object, that rock, even though it's one rock, so you did one realization, some macroscopic quantity is itself an average because it's the average of that quantity in a little piece of the rock, the next piece, the next piece, the next piece, that are all macroscopic pieces. And so there is a notion that even though you take one coupling, in practice, to compute macroscopic quantities, you can always say, I have my piece of rock, which is 1 kilogram. It's the sum of 1,000 grams. Each gram is macroscopic. And each gram, I made a random set of couplings. And so to study this kilogram rock, I made a sum of 1,000 terms of 1 gram. And for each gram, I randomly pick J's. And so you are instructed to compute things and average over those couplings. But what you want to do, again, is very important, is you compute a physical quantity, and then you take that result and you average over the couplings. That is not the same thing as saying the couplings are dynamical. It's not the same thing as saying I sum over the couplings. So in other words, what we want to do, what is correct, is to say what is the free energy, to extract the free energy. I want to take logarithm of my partition function, or if you want to keep the right definition, it's minus the temperature times log of my partition function. And then we want to average this. Right? So this is what's an extensive quantity, like the entropy or the energy or something that I use to compute physical quantities. And then I average this with this probability distribution P. This is different from saying that Z tilde is equal to, I take Z and I further integrate over the product over this probability distribution. So this would be thinking of these J's as dynamical. This would be like saying that my configurations are equal to the spins and the J's. And they are dynamical variables that I sum over. That's not true. That's not true. My rock is my rock. It's not vibrating and moving. It's not lava. It's a rock. You give me a rock, and it's one rock with one realization. I don't average. They are not dynamical variables. So what I do is I look at that rock. I take 1 gram, and I study it. And I take the next gram, and I study it. Then the next gram, and I study. And therefore, I can average over the energy of each piece of the rock. And I can do this. Okay? So this is what is called, when you have these J's, because you see it's random, they are called disorder. And this is what's called quenched disorder. And this is what's called annealed disorder. Which I don't know why they are called these names, but okay, it's just correct and wrong. Okay. Good. So that's very important. So what we want to do is compute this free energy. And so this answers the first question. What is the definition of this quantity here? I just gave it to you. Take this model of spins, compute the partition function, average over this distribution, so that now this doesn't depend on Jij's, it's just a function of the temperature. And that function, the claim is that it's equal to that equation. Okay. So that's the claim. So now you understood the claim, and we are going to derive that claim, but that's the claim. So the claim is that F is equal to this equation 1. So just before, I just want to emphasize why is this problem so complicated? Because you see that this problem even asking, I have this energy, I sum over this. Sorry, I forgot an important factor. When we sum over states, we average it with some temperature, right? So it's beta times this, right? It's e to the minus the energy times the beta. So let this be minus the energy, so there's a beta there. So even when beta is huge, which is low temperature, and you want to say, what is the ground state? What's the configuration that minimizes the energy, right? Is there a unique ground state? Are there many ground states? What's the ground state? And the ground state can be quite complicated, because imagine I start with the ground state, and I say, this spin is up. What is this spin here in the ground state? Well, it depends. If J is positive, to make the energy negative, you want this spin to be opposite. So this spin would be negative if this J here is positive. So I got the rock, and J was positive, then this spin wants to anti-align. It wants to be negative. Now, let's suppose that this coupling here is negative. Then, what about the next spin? The next spin wants to be negative as well in that case. Right? And now, let's imagine these two here, for example, these two to form a square, they are both positive. Well, then, this next one, when I'm here, this next one wants to be positive. But now, you see, the last one is not happy. Right? So this is happy, this is happy, this is happy, and now when it closes, it's unhappy. So you cannot find this optimal energy configuration. And so you get a problem here, and this tension that you get here is what's called frustration. And this means that it will be very hard to find global minima. You will start being happy, but then, okay, it's not exactly optimal. And you will try to do it elsewhere in another piece of the rock, but eventually it's not optimal. And this leads immediately to the picture that probably the structure of vacua and the energetic landscape of this model can be very complicated. And indeed, that's precisely what happens. So if you think a bit about the physics of this model, what you expect is something like this. If the temperature is big, then things are relatively simple, and there is some kind of effective potential where, because the temperature is big, you can jump around between states fairly easily, and there is like an effective minima that is relatively easy to find. Then you lower the temperature, and you could start developing many minima as you lower the temperature. Now indicating that you could be trapped in this local minima, or maybe this one, or maybe this one. Some of them might be easy to tunnel, some of them might be hard to tunnel. Okay? But the temperature is still relatively big, it's still possible to find all this vacuum. But then you lower the temperature further. And now, close to this minima, where there were a million spins, and you could more or less jump over, now you start to be more and more frozen. And you realize that close to this minima, there is frustration. And so actually, this minimum gets resolved, and actually there were more minima there. And you start zooming in and seeing that there is more structure there. And you start seeing that there is this hierarchical structure, that as you lower the temperature more and more and more, you get more and more minima opening up. And this minima, these guys talk to this one talks to this one, so there is some kind of hierarchical structure. And this should make the problem very complicated. And indeed, the claim is that there is a critical temperature, Tc, where this starts happening, and then below Tc, this keeps happening. It's like an infinite sequence of phase transitions. It's not like there is one phase transition. It's like things are complicated all the way from Tc all the way to 0. And this is what makes spin glasses so rich and so complicated. It's really very, very hard to find the minimum of this potential, simulate these models, and that's what makes spin glasses one of the toughest challenges in statistical physics. Okay? Computationally and so on. Even to just simulate these models on computers is very complicated. because you start with some Monte Carlo simulation, for example, and then you are stuck in this minima, and you just don't explore this minima here. Right? And then you start another random Monte Carlo simulation, and you get stuck here, and you don't explore this minima here. And sometimes this might be physics, because it could be that physically you have this metastable vacuum, and your material could be in a metastable vacuum. It doesn't need to be in the optimal vacuum, right? It could be physics. It could take a long time for the model to thermalize to the optimal one. Then you will, for practical purposes, be stuck in a wrong vacuum, and that's fine. That will be where you are. And then you still ask, okay, so on average, in such complicated model, when I compute specific heat, entropy, energy, what should I get? What is the outcome of the experiment? Right? And the claim is the outcome of the experiment is this. Extremize this quantity, and you will get the outcome of this spin glass physics. Okay? So that's the claim. If you want to study this complicated physics, you should study this extremization problem. Okay. Cool. So, so let's derive this expression. So I'm going to erase here. And we'll now do a bunch of manipulations so that we derive that expression. So this expression was derived by Sherrington, and it's this SK paper. I forgot how to spell it. Sherrington and Kirkpatrick. And so that's the paper that I'm not sure if he quotes, but he does, yeah? And so we have to derive a bunch of formulas from that paper that culminate in this equation 1, which is the same as equation 8 of this SK paper with slightly different notation. Okay? So we have to start with, and this, if you want, is equation 1 of this paper. And this probability is equation 2 of this paper. And this is equation 3 of this paper. And so we just need to do the other 5 equations. And then we will be here. Very good. Okay. So equation 4 of this paper is a very important one, and is the statement that logarithm of x is just the limit when small n goes to 0. Here's the origin of this limit of 1 over n times x to the n minus 1. Okay? So that's a true identity. It's just true, right? Is it obvious? I can do it slowly. What is x to the n? It's e to the n log x, which is 1 plus n log x plus dot, 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 when n is going to 0. Right? And so when you subtract the 1, you cancel the 1, you divide by n, and so on. Cool? Okay, so that's equation 4. It's the idea that if you want to get log, why do we want to get log? Log is the source of all our troubles. It's because of this silly log here that we really need to do. It's what makes things hard. Everything would be easy if it was annealed. I'm not even going to discuss. I had it in my notes. Solving this annealed model is trivial. You see why? Because you see, you integrate over Gaussians. Integrating a Gaussian times a linear term, you do it analytically. So you do it. You just integrate. You generate some spin square where spins couple to everyone. And only thing that will matter is the total spin. And you will have a model of just a total spin that goes from minus n to n, and you just write down the solution. So this is really trivial. This would be like 10 minutes in introductory stat mech course. But then you put the log, and it takes 2 hours, right? So log is what really makes our life hard. Okay, so this is equation 4. And then we go to equation, now we combine the log to write equation 5. And equation 5, I will just write it down. Yeah, let's write it down. So what is f? F is, like we wrote there, minus t average over p. Well, average over p means integral over the product of p of jij. Right, that's what the average means for f. And then we have log z, but log z is this. So now we plug this here, and we just write limit when n goes to 0 of 1 over n. And now we are going to write z to the n, right? Z to the n. So I write z n times. Z to the n is z n times. So that means that I will sum over the spins Si equal plus minus 1. But now I will sum with an extra index a, where a takes values from 1 to n. Because I'm just writing n copies of the partition function. I'm just multiplying it. So I'm just saying it's like sum over x, sum over y, sum over z, sum over w, just to write the product of them. And they are decoupled. They are just decoupled. It is just exponential of beta times the energy which is there. So what is that energy? For example, there is the term h times sum over I of the spin Si, right? But now, the spin Si, there are n copies, A, and A runs from 1 to n. You see, decoupled, energy of 1 plus energy of 2 plus energy of 3, it's just decoupled, right? I'm just writing z to the n. Okay, next term, plus another term where I have sum over A from 1 to n, again decoupled energies, of Jij spin Ia spin Ja. Okay. So this is clear, right? This is the same as product over A of a single copy of a free energy. So it's just writing the free energy to the power n. And there was a minus 1. I should put minus 1 downstairs and close the parentheses. Okay, that's it. So that's the beginning. That's the first line of equation 4. And now we can integrate over J, because now the integral over J is it's Gaussian here, it's linear here. So I can just integrate out the j's. Okay, so we continue. So getting rid of the j, we write minus t, and then we put this integral inside, and then limit when n goes to 0, 1 over n. The integral of the p's of 1 will just give me 1 at the end, because these probabilities are well normalized. And the integral in the exponential just gives me the following. Just gives me the summation over all this SIA equal plus minus 1 of the exponential. And now, okay, so the result is a summation over A and B that run from 1 up to n. SI A as J A as I B as J B times J square over 4T square. This was the outcome of integrating the Jij's. So you see you had quadratic and linear, so you have to complete the square and you get a quadratic interaction between. And now, the crucial thing is that now the copy A talks to copy B. So now, different copies talk to each other. That's crucial. Before they were all decoupled, but now we integrated out the disorder and we generate an effective coupling. So that was from integrating the J's. There was this term, and there is still this term that sits here alone, plus H sum over A and sum over I of SIA. Okay, good. So that's not exactly equation 5 because in that paper they did not have H, so I added H to the equation 5 of their paper, but otherwise this is their equation. And yeah, okay. Yeah. Yeah, that's right. So at this point, we are saying, I'm saying that this is like a function of n that I compute from n equal 1 up to infinity, and then I analytically continue to n equals 0. This is not a justified step. It's just the best you can do. If you, otherwise, I could just write partition function to the power n and say n is 0.0001. But what's the second step of the manipulation? You don't know how to continue. So the only way you know how to continue is say, let me assume n is an integer, and then I'll figure out how to analytically continue. So that's the only thing you can do for now is that. Because now you have n copies that talk to each other. What does it mean to say that I have 0.001 copies that talk to each other? It's subtle. So we have to hope that it makes sense to talk about 2 copies, 3 copies, 5 copies, n copies, compute it, and then analytically continue to 0. That's the hope. Okay. Good. Now, what you can also do, okay, I'm not sure how many details I want to put here. Okay, let me maybe, sorry, here I forgot sum over I not equal to j. Okay. Right. Okay. So here we sum over copies A and B, all copies A and B. But notice that when the copy A is equal to the copy B, the result is trivial because you get SI square and SI square is 1. So here I can say summation over A not equal to B, but I pay a constant. There is just up to a simple constant, which is when this is 1, and I sum 1 times e to the j square. So there will be a constant of some simple constant that you compute times this exponential. This simple constant is related to this simple addition here. So that's the simple constant. And then we have this interesting part where A and J are not equal to each other. Okay, so okay, good. Also, here I said I is not equal to j. I can also say I and j without that constraint, because when I equal to j, this is again 1, it's again just a constant. So I put everything in the constant. So I prefer to write it like this. And now, notice something nice that happens here in this sum. So let's call this term, let's denote this term as something. And then this term something, you see that this term is basically the sum over I as b squared, basically, right? Because if you square this term, you get sum over I and sum over j. So basically, we have a sum over a not equal to b of this term squared. And when you have an exponential of some constant times something square, so it would be like my constant a. When you have exponential of some constant times a squared, you can linearize it by saying I introduce an auxiliary variable, d2q, and then I write exponential of minus q squared over 2 plus square root of 2 lambda times qa. Right? So this Gaussian integral just linearizes this. And so you see that this term here is a sum over a not equal to b of some square, right? That I can trivially make it into just linear term, like this, by introducing a bunch of auxiliary variables, q, and we need to introduce one variable q for each AB pair. Right? Because we sum over A and B. And so these are these variables QAB that show up in this equation. Okay? So that's this QAB that show up here. Okay? So let's write it down. So let's continue. So let me write the result down. So the result is minus t, the minus t that's there. Then there is limit. N goes to 0. 1 over n. There is a constant, this trivial constant from these manipulations. And then there are the integrals over this a not equal to b, d this q ab, exponential. I introduce one QAB per each guy, so then there would be exponential of minus a sum one second, let me just do it carefully. This is very important. So let me make sure there is no mistake. Okay, let's just do it ourselves. Okay, so we get these terms here. So for each of them, I need to use this. So I get sum over A not equal to B of Q AB square over 2. So that's this term here. And then we get this term here. So let's write plus. And then that's square root of 2 times lambda. Lambda is this. So I take square root, so I get j over t. So if I get lambda a square, that was a summation of a not equal to j, a not equal to j, square root of that term, and there is a square root of 2, so square root of 2 stays, and then square root of lambda is j over 2t. And then I have q times a, so I get q ab and a is the summation over all spins I of SIA SIB. So here there is summation over A not equal to B of this term. And then the other term that was already in the exponent is plus H summation over I of SIA. And then, after I do these integrals, by the way, there is a number here. And then I subtract 1. Help me out. Did I forget something, or does it look correct to you? Thank you. So there was a beta here that I was missing. And there was a beta. That's it. Then presumably from there to there I did not miss a beta, right? So that's it. Okay, any other, do you define, otherwise do you agree? You should not agree because I forgot something important. I forgot the summation. Where can I put it? And then there is the summation down here over all the spins. Correct? Okay. Now, let's see what happens here. What happens is that you see that here in the exponent, I got a sum of Hamiltonians for each spin I. The spin I is factorized. I get the same sum of energies just for each I. There's no coupling between I and J. And so basically, I can do the following. I can totally ignore this I, right? And I can sum only over SA is equal plus minus 1. But this partition function, I ignore the I, I ignore the I, I ignore the I, and there is just a factor of n. Do you agree? Because it's just a product of each term. Each term, once I sum, I just raise that to the power n. So in other words, I can write exponential of minus sum of QAB square over 2. And then the summation over the spins, I can write, it's just the summation over this SA equal plus minus 1, exactly what shows up here, this summation here. Let's even use this notation, because we already introduced it there. That's what we call trace. So this is just that notation over here. And then trace of this quantity, and all this is raised to the power n, because it just repeats for each spin. This happens. Clear? Mm-hmm. Yeah. Okay. And now, so you see that say again, please. Good, good, good. You don't have the sum over I, exactly, yeah. That was the point. Now it's just a system of small n spins. There's no big N. It's like I, you got rid of it, you keep only the copies, right? It's only the copies talking to each other. And so you have here a mini, you could call this thing here a mini partition function, right? So you went from n spins to small n, and for a small partition function z. Now instead of having n spins and n small n copies, a lot of them, now you only have small n copies. So if small n is 5, you have 5 spins talking to each other. Much, much simpler than a big thermodynamic system. Okay. And now, what is the connection between this and this? It's almost the same thing. It is just a statement that now this integral over q's is dominated by saddle point. And so all I do is I extremize over the q's. And when I extremize over the q's, I go directly to this expression. Just a statement that the integral over the q's is dominated by saddle point, and you just take logarithm of this saddle point. Right? Logarithm of this exponent. You divide by n to write down the free energy per n, and that's why n disappeared, and you get this expression here. Yeah, trace to the power n, ta ta ta. Okay, perfect. Okay. Okay, and that's how we go to this expression. So that's saddle point of this expression here. And now, so now we ask, how can we use this? What should be the intuition? What's going on? We have here n copies, and this Q matrix is a matrix that is coupling the various copies. And you are finding some extremum values of Q's. You could even ask, what is the physical minimum of that extremum value of Q? If you were to compute this extremum value of Q, this optimum value, you would get some QAB star optimal from extremizing this quantity here. What is this quantity? And this quantity, you can see, is the following. So let me write an equation, and then I'll tell you how to derive it. But this is nothing but related to 1 over n summation over I, expectation value of spin I in copy A times spin I in copy B. So it tells you how various copies are coupled to each other. It's as if you had two rocks, and you have one rock, and you ask what is the average spin as I go along the rock. Notice that the total rock might have 0 magnetization, but still in that rock I could ask what's the average on each position. And I ask, if I have another rock, how correlated is it? If in this rock there is a region where it's mostly plus, what's the chance that in the other rock it's also almost plus? And if they agree in some region, how likely is it that they agree in some other region? So it's a correlation between different rocks. And so that's what this Q star would be. How do you see it? For example, when you have this extremum condition, you are doing a path integral over the Q's. So if you change variables, Q goes to Q tilde, you do nothing. You are just doing a path integral. So you can, for free, insert here delta delta Q, and the result is 0. If you change variables here, that's how you derive anomalies in quantum field theory. You just say, I have my path integral, I change variables a little bit, nothing should change. But if you apply delta delta Q, what do you get? When you act on this, you get Q downstairs, and when you act here, you get S times S. So that's how you derive that Q is the interpretation is S times S. Okay? And so this Q starts to tell you that this Q is kind of correlating different aspects of my rock. How I have two different rocks and how they could be related. Now, of course, I'm talking about different rocks, but here, these copies, these n copies, was a trick to get the log. But on the other hand, we have this picture that if I have different rocks, there is some hierarchical structure. That there are some rocks that are close here, and this rock is very close to this one. And it is close to this one as well, but far away from this one. And there is a hierarchical structure. Right? And so this motivates the idea that this Parisian ansatz for this QAB. And the question is, can I make an ansatz for QAB that is related somehow to this hierarchical picture? And that could be a good guess for what this QAB is. And if I make a good guess, then I can try to extremize it with that guess. Because it's crucial to have a guess to be able to continue doing the computation. Otherwise, you don't know how to use this formula. It's too hard. If I tell you, find the optimal matrix Q, and then take the limit n to 0, you just cannot do it. It's beyond what humans can do. Right? So we cannot solve this problem. So we need an ansatz. And what Parisi did in his beautiful paper is, inspired by this hierarchical structure, he came up with an ansatz. But before we do it, this will still take a little bit. Let's see what would be the simplest possible ansatz you could make. So suppose you want to solve it. What would be the most naive thing to say about this Q? Well, you said that we introduced all these copies, and now I'm looking for the extremum. All these copies are equivalent, so the most naive guess is that nothing depends on the index of the copy, because things are just all equivalent. Right? So that's the obvious thing. So obviously, this extremum, QAB, the naive guess, the naive but very natural guess, is that this QAB is just some number Q. Notice that QAB only makes sense when A and B are not the same. If QAB, for equal QAA, we define it to be 0. And now we say Q12 should be the same as Q13 and the same as Q24. They are all equivalent. Why would they not be the same? Right? If you have to make a guess for what this matrix Q is, which is a symmetric matrix, right? It's a symmetric matrix, right? QAB. Symmetric matrix with 0 in the trace. What do you guess? The extremum matrix. All elements are the same. 1, 2, 1, 3, 1, 4, they're all the same. All right? Okay, so that's the, so QAB equal to just some constant Q. This is called the replica. Replica are these copies. Replica symmetry preserving ansatz. Or, if you want, it's the SK solution. So SK solution, go to equation 8, that's either equation 8, and then they continue saying, now it's obvious that the extremum is when QAB are all equal to each other. And that is wrong. So that's where the paper goes wrong, but it's not so wrong, it's almost good. But it turns out that this ansatz is wrong, but it's the most obvious one. So let's explore it a little bit. Okay. Let's do it here. Okay. So now the idea is we try to find F when we have symmetry as the extremum when I replace QAB by small q of that expression, of T times this expression, which is minus beta squared over 4 plus. And now, limit when n goes to 0, 1 over n. And now, see, the first nice thing starts to happen here. So here, we have this sum over a and b of q squared. But q is just a constant, right? And so, this sum here, by the way, this sum, let me just check, is it over a and b or a not equal to b? It's over all of them, okay. Okay, yeah. This is over all of them, but we said that a is equal to 0. So I can say it's over a not equal to b, right? And so, what does this sum become? Q I get out of the sum, and then how many terms do I have? Sorry? Right. So this just gives me beta squared over 4 times q squared times n minus 1 over 2. And then we go on and we try to continue. Then the next one is minus logarithm of the trace of this exponential of, again, this QAB, that is beta squared times q. They are all the same. And then I have summation over a not equal to b, but I will sum over a and b, but that means just SA squared. This is the sum over a and b. And I need to subtract the diagonal. Minus, when a is equal to b, I get s squared, which is 1, minus n. Yeah. let's see. So if n, yeah, okay, maybe there's no over 2. No over. Okay, very good. That's the boring part. This is the interesting part. Then we have this term here. Do you agree with this term? This is more interesting here. Okay. Plus beta times sum of SA times H. And now we would like to do the sum over the spins. How do we do it? How do I sum over the spins? Well, let's use the trick that we used before. Let's write this as logarithm. And now I have exponential of something square here that I don't like. So I trade this by integral d to z e to the minus z squared over 2. That's the trick that we use there to get rid of the square term. And then we write, we also take out the terms that don't depend on the spins. Let's take them out. Minus beta square qn. And then there is trace of exponential of square root of this term, so beta square root of q times square root of 2 times z times sum over a of SA plus h that I put here, plus h times beta. Do you agree? But now, this is just decoupled. The energies for each spin is just totally decoupled. I had the trace. This was this 2 to the n sum. But now they are all decoupled. So it is just a partition function for one spin. It's either plus or minus. In other words, the result of the spin is just hyperbolic cosh of this expression for each of them times 2. And that I raised to the power small n. This is downstairs, right? It just looks upstairs. It's okay? This should be written in this line. It's a bit up in the exponent. Is it clear? We just did the sum. You see, now, this was a huge victory. N is analytic everywhere. We have the limit when n goes to 0. I forgot an exponential here. No, that was already for the free energy, sorry. So it was okay. And then there was this. And yeah, the minus 1 was already, we already got rid of it. I think this is all good. Yeah, this is all good, yeah. Okay, and n is now totally analytic here. And so now you can just see this expand this in n. So all I did here, so this part here is equal to this. And now you just expand in n. For example, this term here to the power n becomes 1 becomes just, if I write it, 1 plus n times log of this plus order n squared, right? And I just expand the rest in n, and I compute what the free energy is. And the final result that we get when you just take the linear term in n, so first you will see that the 1 over n terms will all cancel. And the final result you will get is the following, is that the free energy per n is equal to the following simple result. You get T, and then you get minus J square 1 minus Q square over 2 T square. I'm going to add, okay, sorry. Beautiful. Let's see. Okay. Minus 1 over square root of 2 pi times integral dz e to the minus z square over 2. This was from this integral here. Logarithm of 2 cos of j square root of q z over t. Yeah, I think this is good. So here I did h equals 0 for simplicity. Otherwise, you can reinstate h. And so what we get here is this free energy. And that's the free energy as function of Q. But now you want to extremize this over Q. So you get the equation that Q is equal to 1 minus 1 over square root of 2 pi times the similar integral dz exponential of minus z squared over 2. It's just derivative with respect to Q of this expression. And the derivative of this log, you take derivative with respect to z, then you integrate by parts once, you get 1 over cos square of the same argument here. And so the idea is you have to solve this equation to find the optimal Q and plug it here. And that would be the proposal. So this would be the free energy. And then you could ask, is this right? Is this the correct result? Is it true that the free energy is equal to this, where Q is the solution to this equation? And the answer is no, this is wrong, and S and K knew it was wrong. And they knew it was wrong because they said, let's study what happens at very small temperature. So let's look at very small temperature. At very small temperature, this explodes. And so this cos simplifies. And here, this sesh simplifies, becomes very small. So because this 1 over cos becomes very small, this Q is very close to 1. And so this free energy, you see this term is going to 0. This guy is going to simplify, and you can just expand it at very small temperature. I'm not going to do the details, but I'm going to write what the result is. The result that you get is that F over N is 0.79 plus 2 over pi times t plus dot, dot, dot. Okay, so that's what you get. This 0.79 is just some number that is some square roots of pi's and so on. It's known analytically, but I want to write it like this. So that's what you get if you take this and just expand it as t goes to 0. And this is terrible. And it's terrible for the following reason. Because if you look at what we wrote in the very beginning, remember, what was the entropy? The entropy was the derivative of the free energy with respect to the temperature times the minus sign. And so it means that this tells you that the entropy at 0 temperature is negative. So this would give you that S of 0 is minus 2 over pi. Also, at the time, this is not in the paper, but it was done shortly after the paper, people did numerics for this model. And this guy here, what is this? This is the energy. So this is the entropy, And this here is the energy at 0 temperature, the ground state energy at 0 temperature. And this one is clearly problematic. In fact, what we would like is to get 0. We would like to say the ground state has 0 entropy. There's like a ground state or a few ground states. We don't want something negative, for sure. But this one was also a bit problematic because numerics, Monte Carlo, said that the result should be 0.76. So you see, it's not so bad, right? 0.76 and 0.79 is like a 4% error. It looks like maybe the numerics are wrong, but maybe not, because you do have a negative entropy. So you should be a bit suspicious. Maybe this is not optimal. And so that was the status. And as you can imagine, it's a puzzle. So I mean, you see, this is a beautiful paper of SK. You managed to write this beautiful equation. What's wrong? And for example, when they saw this negative, they said, oh, it's probably this analytic continuation in N business. This was tricky. I had to analytically continue in N, expand in N, and we commuted N going to 0 with capital N going to infinity. We commuted these two operations. That was the natural guess. That's the subtle step, is the analytic continuation in N. Of course, they did not doubt the symmetry breaking. We just had N copies. Why would Q12 be different from Q23, be different from Q34, and so on? But that was actually the wrong thing. The wrong thing is not the analytic continuation. The wrong thing is assuming that these Qs are all the same. And so, just in the remaining part, let me say, so what is the correct thing to do? The correct thing to do is to think more carefully about what is this matrix Q. So this matrix Q it's an n by n matrix. And so Q, we thought of it as a matrix that has zeros on the diagonal. This is our matrix Q. And then we said, this is n by n. Okay, so n is going to 0, but okay, let's ignore that. And then we said that off diagonal, it was equal to Q. Let me call it Q0. And now the idea is to think, no, let's do something else. Let's say that, okay, let's imagine that let's divide n in blocks. So let this be of size. Let me make sure I use the right notation. The biggest one is mk plus 1 is n. So this would be size m capital K. And you see that here, what we have is the following. The total matrix has size n. And I said that I wrote, I take n, and I divided it in blocks of size m capital K. So this is an integer. So that's how we start. So we start with n equal to some big integer. Just to visualize, then we will analytically continue. And then I define mk to be, for example, 10, and I further put blocks here of size 10. And then the idea is that outside these blocks, for example, it could be 10 or it could be n over 2. And if it's n over 2, there are only 2 big blocks. So this would be an example. In this example, this is 4 in the example. And then we say that the matrix Q is Q0 here outside these blocks. But we say that inside these blocks, it's Q1. But that's not the end of the story. The idea is, moreover, take this block and repeat the same story. Take this block of size mk, take each block of size mk, and divide this block. For example, let's divide each of these blocks here in 2. And so now, this guy would be m capital K minus 1. And now we divide this in blocks, and now we have that m capital K is divided in m capital K minus 1, which is an integer. So we further break the blocks into even smaller blocks, which in this case is equal to 2 in the figure. And what do we do in this block? In this outside region, it's Q1, but in this inside region, it's Q2. Okay? And here it's Q2. And here it's Q2. And here it's Q2. And here it's Q2. So you see that we have this region where here it's Q2, here it's Q2, here it's Q1, and outside it's Q0. And the idea is, and this is an example, so here, this stops if capital K is equal to 2. So then we stop, then we say that we stop, because we say that the smallest possible block, if K is equal to 2, now we already have block 0, block 1, block 2, and then we have K is equal to 2, it's M1, and M1 over M0, and M0 is defined to be 1, and this N you can define as M capital K plus 1. So you see that you have 1 up to N. This one, 1 is the smallest possible block, it's just the diagonal, which is 0. And this is just an integer, which would be the size of this block here, the size of the smallest block. And so if K is equal to 2, this is the ansatz. Instead of all elements are 0, are Q0, no, these ones are Q0, these ones are Q1, these ones are Q2, and so on. And why do we like this ansatz? Precisely because it reminds of this hierarchical structure, where we are saying we have a matrix where this 0 talks to the 1s, and the 1s talks to the 2, and the 2 talks to the... And so you are inside the matrix, you recreate this picture. So you think that the degrees of freedom related to this stuff is like Q0, and then the degrees of freedom related to this level would be like Q1, and the degrees of freedom encoding this next level of detail would be like Q2, and so on. And presumably the idea is that this stops here if K is equal to 2, but the good ansatz would be for K equal to infinity, when you take K to be very big. And so you would write an infinite by infinite matrix with more and more and more and more blocks, compute it. And now, what this would become is now you would be extremizing over these values, QA, and over the sizes of these blocks, MA, or if you want, about the fractions that they use, which would be XA, that you would think of as a real number. And so now in your ansatz, you have two sets of real numbers, the Q's and the X's. So these are our parameters. And now we have an ansatz with two K parameters. But for each choice of K, you can still do this type of manipulations. You just have to see that in each block, instead of n, n minus 1, you get m, m minus 1, where m is the size of the block, but the block is a fraction of n. So it's still an analytic function of n. It is just a more complicated analytic structure, where at the end, you will not get an integral of log, but you will get integral of something like, there will be, for example, cosh to some power x, and then there will be log to some power 1 over x, and there will be a bunch of nested integrals coming from the nested structure that I have there. But you get a very explicit expression that you can look at your paper, for example, equation 11 for k equals 2. It's a very explicit integral that you get if you repeat this analysis with level 2. And the idea is now minimize over these parameters. Instead of minimizing over q, extremize over this. And what do you get? So let's just finish by writing what's the result that you get if you now do numerics with this. Right? And so now we do k equals 0, 1, and 2 numerics. I also found k equals 3 numerics in the book that I got yesterday from the library. So we could ask, let's see what the numerics give for k equals 0, 1, and 2. 0 is what we just did. And then you ask, what is the free energy at 0 temperature? What is the entropy at 0 temperature as a function of k? And as we see, when k equal to 0, we got this 0.79, and the entropy was minus 2 over pi, which, okay, which in numbers, how much is 2 over 5, 2 over pi? So this 2 over pi is 0.16. And then when you do k equal 1, this becomes 0.77. You see, much better compared to the numerics. And the entropy becomes minus 0.01. And then when you do k equals 2, this becomes 0.76, exactly as the numerics indicate, and the entropy becomes minus 0.004. So it's obviously what's going to happen. As k seems to increase, the evidence from this paper is that this is exactly what the numerics give. I'm converging the energy towards the numerical energy. In fact, he predicts what the energy is with 4 digits. Which is super hard to check numerically from Monte Carlo, because as I said, these problems are full of spin glass behavior. It's very, very tough. And so he predicts what this should be with like 4 digits. And then if k equals to 3, you can check how many change. And you can see how this ansatz is very quickly converging towards this value. And the entropy is just becoming smaller and smaller. So it seems like the entropy is converging such that when k is going to infinity, you are going to reproduce the correct physical value, that the entropy is 0 for the ground state, and that this ansatz is correct. So this seems to be the good ansatz. If you want to take n by n matrices where n goes to 0, this is the obvious ansatz. instead of saying that Qij is independent of I and j because the copies are all the same, no. You should say the correct ansatz is this hierarchical fractal structure. And that's the second, that's of course your second guess, right? And, and indeed, your second guess would be correct, it seems. And, but of course, it's by no means proved. I mean, this is just full of assumptions. And this field of statistical mechanics of spin glasses, my understanding is that it's a field where mathematicians and physicists really like talking to each other because physicists come up with these crazy conjectures, or this is probably what you should do. But the problem mathematically is super well posed. It's just sample from these distributions and compute this quantity. It's really something super well defined from probability point of view. And then what is the way to compute is with some analytic continuations of logs and some hierarchical structure and some fractals and so on. So, and so mathematicians try to see, can they make this rigorous? Can they put bounds on what this U of 0 should be? And can you prove why this ansatz is correct? And so on. Can we analytically derive what happens when k goes to infinity? Yes, and there is this beautiful differential equation, but I'm not going to describe it there. So I think that really the main thing of this paper is really this picture here for this ansatz that says that this Q, whose meaning, like I said, was the coupling between different copies, that says that for the most part, different copies are the same, but then these ones are more similar to each other, and they talk a little bit more to these ones, and a little bit less to these ones, and a little bit less to these ones. And so they try to encode this ultra-locality of the spin glass, of this landscape, into that matrix. And so it's a nice inspired guess, and the numerics are very impressive, so it's probably a good guess. So that's a prototypical example of a spin glass, and this is what's called replica symmetry preserving, and the other one is what's called replica symmetry breaking. Because you started with a model where all replicas were the same, so there was an obvious symmetry, which was rotation of the replicas, but apparently the solution breaks that symmetry and says, no, the correct solution introduces this hierarchical structure, and that's why it's called replica symmetry breaking ansatz. Okay, I had warned that this was a bit tougher. I think it's conceptually a bit tougher, so I don't know. So now we need a volunteer for next week. Who would like to volunteer to Marvin? Very good. Okay, so Marvin will tell us something about some modern paper that discusses these ideas of replicas and replica symmetry breaking, yeah. And next week we do, it's the last lecture, and yeah, next Tuesday, we do Tuesday normally, and I'll be describing Witten's paper on ADI-CFT. Yeah. That's an advanced paper, but it's very pedagogical. I think it's easier than this in a way, yeah. Yeah, usually on Tuesday, 10:30, yeah. And it's the last one, yeah. No, that's not obvious, but you could do a low energy expansion of the model in the same way that in statistical mechanics, it's one of the tools people use, a low energy and a high temperature expansion. A bit like what we did in the Ising model in one of the first lectures. And Anderson and Toulouse had done that, and they had not only, they knew it was going to be 0, but they know what this term is with t square, and they know what the coefficient should be. So this low energy expansion, the entropy part is actually derivable from a low temperature expansion of the model. You can, so that was a numerical check that he also does in the paper. Not only it should vanish with t, but the t square term is known. And he can check that as you increase k, it's going to go better and better. But that's not guaranteed, because as we said in the beginning, there could be many, many vacua. The number of vacua could grow. On the one hand, you want to freeze. On the other hand, there are many configurations. Which one wins? So, and in this case, it turns out that even though it's true that there are many vacua, when you really freeze the model, the entropy is effectively 0. They don't grow as fast as to give some finite contribution. It's specific to this model. There could be models where it's, but it could not be negative. So what this tells you is that in this ansatz, it goes to 0, clearly, right? But imagine the physics was that it should go to 1/2, then clearly this ansatz is not good. But the numerics indicate it's 0, it's okay, and that is going to 0, so it seems to be okay. But that's the norm, right? In physics, the norm is that the ground state has 0 entropy. The exception would be models where there are so much degeneracy. Typically, the degeneracy is in the excited states, not in the ground state, right? In the ground state, the number of states don't scale with n. They can be, maybe there are 100 ground states, but not 10 to the 23 ground states. Yes?
When you take some like arbitrary value of k, does Q0, Q1, Q2, how do the values of Q behave?
So what happens is that the values of Q, so they behave like this. So Q, they are all between 0 and 1. That you can show easily. And indeed, if you remember the definition of what Q is, that's obvious from the definition, because Q was the sum over spin at position A, spin at position B. So if the correlation function is the same, it's 1. If it's completely opposite, it could average to 0, but it's between 0 and 1, clearly. And so what you can do is you can define a function Q of x, which you define to be a function that is QZ, QK, and then QK minus 1, and so on. A step function that goes from 0 to 1 in this variable x, which is m over n. So you just define a function that, as I plot it, when I reach the first block, it changes. It's just a way of encoding all this function.
It is increasing as you go deeper in the matrix.
It's increasing as you go deeper, because, yeah, it's increasing as you go deeper. And then, so he plots what do you get for this function, and he sees that for k equal 1, he gets something like this. And then he does numerics for k equals 2, and he gets something like this, because there are one more step. And then he says, my guess is that for infinite k, the function is probably something like this. And it's an educated guess for what this function Q should be. And then you could ask for this free energy as a functional of this function Q of x, and plug this Q of x here, and you get some very good numerics. Yeah, so there is a function that codes this hierarchy and how things are changing as you are moving in closer and closer to the diagonal. Yeah, that's it. Yeah, so this was a tough paper, no? Did you struggle when you were trying to study it, or was it easy? Does someone work on this type of topics? You a little bit. Yeah.
There you get a large constant
For SYK. For SYK, yes. Yeah. Yeah. Yes. There is a lot about that in this field, yeah. Because as you can imagine, the late time behavior is going to be very different in these models because it's very hard to thermalize because there are so many metastable vacua. So there's very interesting universality, but different from the standard one about late times, precisely because you will be stuck in the wrong places for a long time, then eventually tunnel, and so yeah, it's very interesting. I think people sometimes call it aging and so on, but yeah, what we did is like the first few chapters of this book, for example, the theory of spin glasses and neural networks, but then some chapters are about aging, some chapters are about experiments. There are partial annealing when, for example, you do have a piece of lava where it's not completely dynamical, but it's sort of dynamical, and or you could have just annealed, but then it's trivial, who cares? Then this type of models, people apply it for neural networks as well, where you think of a bunch of neurons that are coupling, and you can ask, can I couple all these spins to some other set of spins? And this other set of spins would be like images that your brain sees. And how you couple now these random spins with some other set of random spins that are some image. How is that image going to influence the background structure, the ground state structure here? So the model plus coupled to Mickey Mouse, does it change the structure of the ground states such that the image of the Mickey Mouse is secretly in the landscape of the ground states, and you see the Mickey Mouse in this matrix? Because this would, if so, this would be a robust way that the brain could work. Because you could just see an image, see many images, and there's so much space in this 0 by 0 matrix that all your memories could be there. So you just need to hide them correctly, and depending on how you probe your neurons, you would extract different memories.
Is there any mathematical intuition for why there's so much space in 0 by 0 matrices? Why the K-equal infinity answer is a good answer?
Mathematical or physical? The only thing I would say is that as it's not so much about 0, but about being not integer. That matrices are linear maps. And those linear maps, they act on some finite dimensional space. But when you say, I lift the requirement that the space is finite dimensional by going to non-integer map, then I'm exploring like infinite dimensional linear maps. So it's a bit like representations of integer spin versus continuous spin. And sometimes it's the case that integer versus non-integer means finite or divergent, right? It's like delta function normalized or Kronecker delta normalized. And so I think here it's more the idea, it's not so much that it's 0, but that it's non-integer, that you approach it from non-integers. And then it's a subtle tension. You want to go to an integer, but you come from non-integers. So should you still keep infinitely all this infinite structure, or will some of it collapse? Because there are other analytic continuations. When you do continuations of these matrices, not to 0, but to 1 and other values, to study other problems, like percolation, it's often related to n equals 1, and other things. And I think similar stuff happens, that you have all this structure. Yeah, but what's the mathematics? I mean, we are doing limit of n goes to 0 of something that clearly only makes sense for integer n. I mean, there's no mathematics, right? It's wild territory. I mean, we can do it because we are physicists, but, but there are no rules. It's a Wild West.